Chen. Congress has aggregated several researchers from all over the world. And for example, we have a second event today here in Cádiz. This is a workshop on jellyfish. This coincidence has a negative effect on the audience here, as you can see, with several researchers attending the other meeting. Well, Robert Chen is a professor in the School for the Environment and is also the director of the Center for Coastal Environmental Sensing Networks at the University of Massachusetts, Boston, a university with important links with the University of Cádiz and with ceiMar. Professor Chen graduated at Harvard University in chemistry and physics and received his PhD in oceanography from Scripps Institution of Oceanography. After a postdoctoral fellowship at the Goodhull Oceanographic Institution, he has remained at UMass Boston since 1993. His research interests include carbon cycling in coastal waters, contaminants in urban harbors, and the application of coastal sensor networks to societal needs. He is also dedicated to ocean and environmental science education and outreach at the local, national, and international levels. He led the Watershed Integrated Sciences Partnership, the COSI Ocean, the Boston Science Partnership, and the Boston Energy in Science Teaching projects. He is currently a co-PI, principal investigator, on an National Science Foundation informal science education project on climate change. As most of you know, this afternoon he will pronounce another talk on education in sea science, but now the title of his actual conference is Coastal Carbon Cycling. I thank you very much for coming, and with all of us, Professor Robert Chen. Thank you.
Thank you very much for that. So thank you so much for coming today, and thank you for having me. Have any of you been at the Oslo conference? Ah, yes. Very good. It's an honor to be in Spain, in Granada and Cadiz. And I apologize that I have to speak in English. Spanish is not good. I'm going to talk to you today about coastal carbon cycling. And I want to say that coastal systems, estuaries, salt marshes, mangroves, are very complex systems. The problem with them is that each one is different. And many of us that study coastal systems will study one system, but not many systems. And to be able to scale to global scales about the importance of coastal systems, we have to begin to try to figure out what are the main issues with these different coastal systems. The problem is that the temporal variability, the change in variation in time, has tides that move in and out on the hourly scale. So if you sample a bucket or a bottle at one time, at one place, an hour later it's a different water. The river that flows into an estuary can be dry, can have an average flow, or there can be a rainstorm and it can come flushing down and change the dynamics of the system dramatically. And if we think about chemical spills and oil spill, we need to know right away where it is, when it is, and where it will go. So we need this very high temporal resolution. In terms of spatial resolution, it also varies dramatically within meters. The bottom of the estuary is something that we need to understand and know. And I'll give you one example, but the water flow might flow one way at low tide and a different way at high tide. The ocean, coastal ocean, is connected to the land. So we need to know what's happening in the watershed, land use, urbanization, development, aquaculture, to know what's happening in the water. And a lot of times there are multiple sources of river or contamination, or there's agriculture and urban, and they all come in, and a lot of times we need to know from the local people what is happening over time in terms of the sources. So to give you two examples, the first is temporal variability. Here is the tide in Boston Harbor. It's about 3 meters, the tide, up and down every day. and it goes in a sinusoidal curve. So you might expect that if you monitor the chemicals over tides that you can model as a sinusoidal curve. But it's not true. This is just simply salinity. So if you look, it's constant, and then it drops very quickly within minutes to a lower salinity, and then it rises slowly back to the other. So if you think that it's going to be sinusoidal in your models, you're wrong. Why? Because in this case, here's UMass Boston. The river source is here, and there's a mussel bed. So it's exposed at low tide. So as the tide rises, it needs water to fill the basin, but it can't pull from the ocean. It can only pull from the river. And so then the salinity drops very quickly. As soon as it goes over the mussel bed, then the salt water rushes in, and it goes right back up. So here's a very fast change that is not predicted. And the chemicals here, this is dissolved organic matter, follows the salinity, up and down. High dissolved organic matter with fresh water, low dissolved organic matter when the seawater's in there. The other example is, this is the Neponset estuary. It's very shallow, 2 meters depth. 2 meters. But of course, 3-meter tidal height. Okay. And this is the fresh water. This is measuring, I'll tell you more, this is measuring dissolved organic matter fluorescence, CDOM. I'll tell you more about that. And here's seawater, which is low in CDOM and high in salinity coming underneath, and the fresh water flowing out on top. And we have an instrument, I'll explain, that makes measurements every dot. So it's very, very high resolution because it's only 2 meters, and it's only 2 kilometers. But what we see in this distribution is that the fresh water comes out and hits a point and pools up here before it can release to the rest of the estuary. Why? There's a bridge. It's a tidal restriction that changes the whole dynamics of the coastal system, which changes the chemistry and the biology. But without the resolution, we wouldn't be able to see that. So we need very high spatial resolution. This is high tide. This is low tide. So now it flows out. You can see it. It traps and then flows out. If you have a question, just raise your hand. So we need high-resolution sensors and systems to be able to see these dynamic, complex systems, just to be able to see them. If we can see them, then we can begin to understand the processes and then make a model. I study chromophoric dissolved organic matter. It's what makes water yellow, or makes tea yellow. And it turns out that if I shine a laser or a UV light, ultraviolet light, it glows blue. Ah, beautiful. Tonic water. Tonic water with quinine glows blue. So I can make a sensor that measures fluorescence that's very small and gives you data every 1 second. So it's continuous. Dissolved organic carbon, I have to take a sample, go to the lab, burn it, measure the carbon, CO2 evolved. This, instantaneous, every 1 second. Okay. And then I have these different systems. I have buoys and ships and things that tow behind ships and sensor networks that are wireless and real-time. So here's the, this is dissolved organic carbon on discrete bottle samples. And here's the measurement of fluorescence from the sensor. Yeah, it's pretty linear over different cruises. Different areas are different. Different times of year, sometimes different. So we always need to take some discrete samples, but then we can make the real-time 1 second sensor, say dissolved organic carbon, a proxy for DOC. So here's a few systems that we've made. This one is called Eco Shuttle. It looks like this. It's a towed vehicle. It has a cable to the ship. It has a wing that we can computer control to say dive or rise or go to this depth and hold or go in a sinusoidal curve. And we can get two-dimensional cross-sections of the surface ocean to about 30 meters. It's special because it has a very big cable with inside a Teflon tube, hose, half-inch Teflon. We get 10 liters per minute of seawater from whatever depth this is at into the lab. So here's the lab. We pump in the water. If we see something in the real-time data, here's a thin layer, here's a plankton bloom, here's a something, spill, we can take water samples. And here's the big winch. We put it on the back. We also like to measure the surface distribution, not just the subsurface. So we have a pole on the side of the ship, and we mount sensors in the pole and maybe also a pump to get water from the surface. So we can do surface mapping and two-dimensional cross-section. It looks like this in the lab. The water comes in through it's a rotary joint that turns, but the water comes through. And then it gets into a distribution system where we can sample the water in the sink inside the van. This is in New York Harbor, Hudson River. We can take the winch and the van anywhere, any ship. And inside is very consistent. The lab looks the same in the Mississippi River, in Europe, in Asia, in Hudson. Looks the same. So we don't need to find anything. And everything is tied down to the bench. So we don't have to remount everything every time we go on a cruise. It's done. We put the van, clamp it down, half a day, ready to go. We took the hoses, the electrical, ready to go. For smaller systems, like the Neponset River, where I showed you that data with the bridge, we have what's called mini shuttle, small one. It's this is upside down. It's a wing, and it depresses in the water. And in the wing, we have sensors, all within 4 centimeters. So you saw the data from the depth of 2 meters. The sensor here and a sensor here is different water mass. So we have to get them close so they're measuring the same water mass. Salinity and CDOM, same, not half a meter different, third of a meter different, something like that. And we tow it off the side of a small ship. We can put a Teflon tube if we want to pump a sample. And if we want to go deeper, we let out more line. We're going to pull it up the surface. We come up. We can go right down to about half a meter, 20 centimeters from the bottom. And we can go right up to 10 centimeters from the surface. So we can get very, very high resolution. And we can mount it on a small boat, 5-meter boat, so it can get into shallow waters. It has a pressure sensor. And so then when we let line out, we can measure 5 meters, 6 meters, and we have a bottom sensor. So if we get too close, we pull it up. And so this is all, these are towed vehicles behind a ship. But also sometimes we need to have just, we need to just watch. So we've made these buoys. It has meteorological sensors, wind speed, direction, rainfall, humidity, sunlight, PAR, photosynthetically active radiation. And then it has a well that goes into the water, measures temperature, salinity, oxygen, CDOM fluorescence, chlorophyll fluorescence, optical backscatter, all these things. The data comes in and then gets sent by cellular phone. Every 15 minutes, we get data point. And so if a storm comes, we don't have to send the graduate students out in the storm. We can just watch and listen. But as part of a sensor network, these things can be watching. Here comes something, and we send out the ship, or we send out an autonomous underwater vehicle, or we sample automatically many things. So it's these 3 things, temporal and spatial. So I'm not sure if I have enough time to do all 3, but we'll try. 3 examples of some of the applications of these systems. The Mississippi River plume, the 7th largest river in the world. Boston Harbor, this very small Neponset estuary, and something about how land and ocean is connected. And salt marshes. So the new research I'm doing is about a small salt marsh in Florida. So the Mississippi River is the largest river in the U.S. It covers 41% of the land area. It drains through into the Birdfoot region in Louisiana, USA, and it flows out and causes the dead zone. So many nutrients from agriculture, then eutrophication, and then fish and low oxygen and fish kills and whatnot. What's interesting about the eco shuttle is we tow behind the ship, and we never stop. So most oceanographers like to stop, do a station, go, do a station, I don't know, maybe take a core. We go at 8 knots, continuously, never sleeping, never stopping, 24 hours a day, always moving. So when I proposed this project to the Office of Naval Research, who funded it, they said, I want 4 days of ship time. I said, no, you need 7. I said, I only need 4. No, you get 7. So I went, and in 3 days we were done. And then 3 more days. Okay, do it again. So it's a lot of land. We can do a transect in a few hours, and then come back and do a transect. We can map the whole. This is the plume of the river flowing this way. The other river coming out here is the Atchafalaya. It's the same water as the Mississippi, but this comes through levees. This comes through wetland. So very different quality of the water. And so we can map all these areas very quickly with the eco-shuttle. Also getting water samples, also looking at distributions. So here's the surprise. So this is the river plume. This is CDOM fluorescence. Fresh water coming out in the plume. There's some variation in the plume as it flows out over seawater. And it's a very high CDOM, low salinity. We can look at the plume and how it breaks off and where it goes, and we can put buoys in it and measure that. But down here, at 25 meters, more CDOM. Not expected. What is it? Where is it coming from? So what we normally think about estuaries and freshwater mixing with saltwater is that we have high DOC freshwater, low DOC seawater. Linear conservative mixing. You just mix the water together and it just goes down. Okay, that's what you would expect if it's conservative, no other sources. This is a river in estuary in England. So what we see is this. Here is a linear mixing curve, pretty much with the Mississippi, but 3 of them. 1, 2, 3. Why? Different ages of the plume. The plume came here, and then the flow changed. The end member might have changed, and then the flow overlaps here, and then the flow overlaps here. It could have been a rain event, has a different DOC composition, and so it has different mixing curves over time. So that's one thing. The other thing is we have this. The high salinity end, very significant dissolved organic matter production, but not from fresh water. The salinity is constant. Where is this? Well, I can blow this up because I have high resolution, and I can track individual dives of the eco-shuttle. I say, here's A, B, and C. And so then I can get individual profiles, because it's vertical profile, each up and down and up and down. And what we find at this depth, where we have the high CDOM, is what I call a density bend. The density is lower, and then suddenly increases, and then goes higher, but slower. So it's like the ocean-air interface is a discontinuity in density. In this case, there's a discontinuity in density subsurface, not so much as water to air, but salty water to fresher water, or colder water to warmer water. And the particles from the river fall down through the water column and rest on the density bench. This is very good food for bacteria. The bacteria come, eat the organic material of the particles, and they produce CDOM, or a certain kind of marine dissolved organic matter. Not the terrestrial particles, but they've converted it to marine isotopes, marine composition. It's a different lability, photochemically, bacteriologically. We can sample that very thin layer, only maybe a meter or 2 thick, because we have the pump of the eco-shuttle. We can pump it onto the boat, and we've done incubations on the water, and it's very different from the water above in the plume. So here's a process that we would not have seen without the very high-resolution tool. We can go back and do this transect and look at it in 3 dimensions under the water. And then we can go back 24 hours later and do the same transect and find how the amount of this excess DOC, the bacterially produced DOM, actually has tidally moved in and out. We went back to the same place. Oh, it's missing. Oh, but it moved over here. Now it's coming back. And then we can take the volume and the amount and estimate how much production of dissolved organic carbon is subsurface, this marine. And we think it's about 15% of the river flux. It's related to the river because the organic matter started as particles, but it's not typical watershed DOM. It's marine DOM. It's about 15%. So we know the river plume can carry lots of dissolved organic carbon and is temporally varying, and now we see the different plumes over time with the end member shifting. The particles can be converted by bacteria to DOC, and we can observe this bacterially produced DOC and estimate how significant it is. Before this study, we didn't even know, we suspected, but we didn't know that the bacteria produced this material subsurface, and we definitely couldn't estimate how much. Questions on that example? The second example is a much smaller scale with the mini shuttle. This is Boston Harbor. So UMass Boston is right here. This is the mouth of Boston Harbor. This is Boston. And inside the Charles River, the Boston Tea Party, the Revolution, all these things. It was called the dirtiest harbor in the United States about 30 years ago. And we had sewage coming out here. We moved the sewage 19 kilometers offshore. We have secondary treatment of the sewage. It's much better treatment. And now Boston Harbor is clean. And these islands are a national park. A very interesting history. You can go visit and see these things. The water quality is much better. The Charles is the biggest river, and the Neponset is the second biggest river entering Boston Harbor. So my study here, it's 5 minutes to go up the Neponset. And we get a salinity gradient. There's also salt marshes there. And we want to look at the communication, the interaction between the land and the ocean. So here's the watershed. There's 14 cities and towns in the watershed. It's about 300,000 people. So there's impacts living there. And it's a very small freshwater flux, but we can measure it very well because it goes over a dam into the estuary. So it's U.S. Geological Survey. We have the flow. Very well constrained. We can sample that. So we want to know what is controlling the flux, the amount and the quality of dissolved organic matter flowing from the watershed to the ocean. And we know that the watershed matters. So it rains on the watershed before it gets into the river. There's different kinds of land use. The temperature changes. The leaves fall in the fall. So then the water filters through the leaves and makes tea. Oh, a lot of dissolved organic matter in the autumn, in the fall. In the winter, it's frozen. Like now, snow this high. Ooh, nothing. Very low carbon, maybe some low water now. It matters if it rains on parking lots or if it rains on forest, because it has different amounts of dissolved organic matter and different residence times. And then if you allow high temperatures, the bacteria can change the dissolved organic, it can respire it or it can change it. Or sunlight, photodegradation can change the dissolved organic matter. So that's in the watershed. Then it comes over the dam into the estuary, and there's a salt marsh here. So tidally, the water washes over the salt marsh and washes back, washes over the salt marsh and washes back. There's some little tiny other river that comes from a street, not really a river, a creek, that comes into the middle of the estuary. And then sort of all of the different things that humans can do. We can fertilize our lawns, we can have golf courses, and can change the dissolved organic matter over time or over seasons. And then it gets out into the estuary in Boston Harbor, and you get tidal mixing, you get photodegradation, you get particle resuspension, we have plankton inputs. All of these things are sort of need to be thought about. So what have we done? Well, we have in the water, we have this mini shuttle. But in the watershed, we send out graduate students. And we send the graduate students out every month to 31 sites in the watershed. Why? Because we use GIS, Geographical Information System, to find what the land uses are. And the main land uses in the watershed, where? are 5. Forest, residential, houses, industry, mostly rooftops and parking lots, wetlands, and 2% golf courses. 2%. Those are the leading 5. And so here's the forest and residential are the big ones. But wetlands have very high DOM, so even a smaller percentage matters. And we can use this plot to figure out where is there a sub-basin, a sub-watershed, that is 80% or more just that one source, just forest, just residential, just industry. And we call those N-member samples. I'm going to get 5 forested sites and see how the forest is responding seasonally to a rainstorm, to a whatever. And then I'm going to find 5 wetland sites that look like wetlands. And so there's some variability, but they might behave similarly. And then so that's about 15, half the sites. And the other sites are somewhere in the main stem of the river that says I have 10% industry, 20% something else, forest, 10% wetland. And then I send, now I can test to see if I have an equation, a model, that can predict what comes from the forest, what comes to wetland. So what would be in the river at this point and this year? So I have to make this prediction. So turns out that if you just assume that DOC is constant over the whole year, and you just measure flow, so flow times concentration is flux, the amount of carbon that flux out, 44% of the variability is explained just by flow. Okay, so that's a good starting point. And how do we measure flow? Well, we have USGS gauging stations at 3 locations, not everywhere in the watershed, 3 locations in the watershed. But I can use a hydrographic model to understand flow everywhere at all times. Okay, so I take these 3 as tests, and I take the area and the slope and the type, land type, all these things, and I can make a model. So here's an example of what goes into the model. It has evaporation and precipitation and soil and slope, groundwater, all these things. It's called the SWOT model, S-W-A-T, SWOT model. And I can put in precipitation and flow. So here's precipitation on the top. And what I have is, which one's which? Black. Red is the measured discharge, and black is the modeled discharge. But the model can give me every point in the watershed, anywhere you want. This is just at the bottom. And it's something like R squared of 0.72. It's pretty good. It gets the main events. It's okay. Not 100%, but it's pretty good. So then I can take that flow, and I can say, I'm going to take the flow at all these different places and then see how I can predict how much this is carbon is fluxed out of the entire watershed. And I can get better than just the flow. The simulated flow gives me better than the measured flow. Okay. Then I say, but I know that the sources change with season. Lots of carbon in the fall, no carbon in the winter. How do I deal with this? So again, the graduate student, a couple of dissertations, were sampling these different sites every month. And they measured, wetland is much higher, industrial is variable, and residential is the lowest of these. So now I have an N member, and I can look for a regression equation because now I have 15 points to test what percentage of each of the N members are in adding up to some monthly value. And here's the major factors that affect things seasonally. So I have this growing degree days. This is the temperature somehow. I have precipitation events. I have snow. I have the type of the land use. And I put these in a regression equation. and I figure out which ones drive the seasonal variability of which end members, land use types, and the model becomes even better. Now I have 0.77 in terms of the carbon measured. This is at the, we call them pour points, where they're coming from the different land use types up in the watershed. And then this is 0.89, good between the model and the observed. This is CDOM, it could be DOC, with different months. So I can test the different months, the different seasons, and I can compare the model. And now I can predict the flux of carbon every month, depending on these 4 parameters: rainfall, temperature, land use. But I also understand a little bit about what the forces that drive the change. So, so now I can say, if I change, okay, so this all started because I wanted to say that this is a minuscule flux of the small watershed compared to the global, if I scale it to global. But the behavior, the dynamics is very different. So if I think about every small system, which is more than half the freshwater flow into the ocean, behaves like the Neponset, the global DOC flux that we have in the global carbon models would be double, because smaller systems transport more carbon than bigger systems. So that says it could be different, could be significant. In the Neponset, if I change from forest to residential, if I develop a watershed, I change by 12% the discharge of the carbon. So I have more from the forest and less from the residential. So if I develop a different watershed, I might expect a similar trend. If I change globally from forest to agriculture, it's a very small difference globally. But at least I have an idea of what it did. If I have climate change of temperature and precipitation, I can now say that temperature will lead to higher discharge, and precipitation will lead to higher discharge of carbon from land to ocean. So because we understood the processes, we can make predictions that can be tested over time. Questions about this part? Yeah. So the sewage is all piped from the Neponset and other towns way out into Massachusetts Bay. So we shunt the system to get out there. In the biggest storms, we have something in Boston called combined sewer overflows. You have? So the sewer pipe is too small, and it would break. So they shunt the water into the stormwater system, which means raw sewage just goes out into the river. But we've eliminated from 200 CSOs in the Boston area, we're now down to about 40. One by one, they make them bigger and fix them or put a reservoir or something. But in the big event, you have to worry about sewage. Normally, you don't see any. But in the big event, you have to worry about raw sewage coming. Or if there's a leak or a break in a town, you might see something. And hopefully your sensors or something would pick up something strange and say, oh, different. The model doesn't work. It's something else. Good question. Anything else? Okay. So recently we've been thinking about blue carbon and outwelling, so salt marshes. So because of many studies we've had in San Francisco Bay and Plum Island LTER, even the Atchafalaya in the Mississippi, we find the influence of the wetlands at the coast is significant in terms of carbon production and carbon cycling. But it's very complicated. It's tidal. There's all these processes. It's tidal. There's groundwater flow. There's very high productivity of the grasses. There's tidal recharge. And there's river inputs. And how do we separate all these different sources? So we chose a little tiny salt marsh called Snipe Creek in Florida because there are no rivers. There's no humans. Very few. There's a few people that fish in there. But really the watershed is just forest. It's high production and as any salt marsh. We have a 1 meter tide that washes in and out. The problem is that it's so shallow that we can't get the boat in there at low tide. So we need some sensors 24 hours, and we go in at high tide and sample, and it's logistically difficult. You can't hike in. It's too far. It's very remote. And we had 4 field campaigns, about a week or 2 each, in fall, when the grasses are going senescent, turning brown and dying, and in April when they're just growing up like crazy. And if you look for this complete carbon budget in one of these salt marsh systems, it's very hard to find, very rare. Okay. So we tried to use many people. To give you an example, I'm a marine chemist, organic geochemist, something. Jay Cable is a hydrologist from University of North Carolina. Jennifer Sherry is a carbon isotope biogeochemist. She does C13 and C14 and bacteria. Christoph Mail is at University of Georgia, and he does modeling, coastal systems. John Shallis is a remote sensor from Creighton University. Bernie Gardner is a physical oceanographer. It's another organic geochemist, an engineer, and then many students. So it's many, many different types of expertise because it's a complex system. So here's Snipe Creek. It's in, we call it the Big Bend region of Florida. So Florida is the bend before the panhandle, before the tail of it. Right up in there is this salt marsh. And here's a small river. And here's a small river, and they're spring-fed, so the DOC is very low. And there we pick a tidal creek right in the middle that's just salt marsh. So we should be very simple. The water washes in, the water washes out. It washes in, washes out, and takes with it carbon. And we can use LIDAR, remote sensing of the elevation. The trouble with the elevation is that it hits the top of the grass. So then we have to send out people to walk and say, okay, this is the top of the grass, this is the bottom of the grass. And we get an offset. And you have to run around in the mud, yeah. And there's wild boar and alligators and things. So we get this offset, and we see the elevation, and we can calculate from the elevation and sort of where the watershed is, what the tidal prism is, how much water flushes in and out at different kinds of tides, neap tide, spring tide, hurricane tides, these kind of things. And then we have Worldview 2. It's a satellite with 2 meters resolution, 2 by 2 meter resolution, and 8 colors, 8 different wavelengths. And then we again send graduate students out, many graduate students, many hot hours of walking around and saying, this is Juncus. This one is Spartina. This one's Juncus. And they make little areas, and they say, here is Juncus. Here is Spartina. This is 5 pixels. Juncus, Spartina, Juncus, Spartina. And they take 2/3 of hundreds of these polygons, and they train a neural network, a model, that says, this is the equation to take these 8 wavelengths and turn it into a vegetation. And then the other third of the data, they test the model. And it's about 87% accurate. Pretty good. What do we learn? We learn that it's 71% Juncus, this very tall one, and Spartina is on the edge of the creek, and that's about 18%. Some combination, mixed, 6%. Sometimes you get a high spot, and these are, for whatever reason, it's higher, and it retains some fresh water, doesn't get tidally inundated, and there's trees. So it's like a terrestrial kind of a thing, 3%, and then dead grass is like 2%. So we can take these numbers and some literature estimates of how much biomass per meter squared of the different species and how much carbon is in each of these dead biomass, live biomass, and we can get a total above ground carbon biomass of our study site being 316 grams carbon per meter squared. But we want productivity. We don't want just standing biomass. And so we look again in the literature and find that oftentimes the ratio between the annual production and the standing crop biomass above ground is 2 to 1. 1.5 to 2 to 1. So we multiply by 2 and we get something like 600. But there's also below ground growth, something additional. We look again in the literature and we find there's a range, a summary of productivities of salt marshes throughout the East Coast, South, and it's between 400 and 2,000, average 1275. So between 600 and 1,500 somewhere is our net primary productivity. We just call it 1,000. 1,000 is a nice round number. It's probably pretty close, within 20%, and it's a multiple of 100%, so it's very easy for, for me to look at. Now we do a bunch of experiments to see what the sources of carbon are in this system. One is we take the plants, the juncus, the spartina, and I'm not even going to talk about it, but the seagrasses offshore, another source, but we didn't measure anything, and we put them in the water, and we let the organic carbon leach out as DOC. Just make tea for 25 days. And we find that somewhere, depending on the species and the season, 5 to 25% leaches out as DOC. That's a lot. As the plant dies, and then 25% can come out in the water. The average for juncus, which is the main grass, is about 8%. So if we assume that 8% of all of the primary productivity turns into DOC at some point and gets leached out into the waterways, then we have a number of 80 grams carbon per meter squared per year for our system. Started with 1,000, and this is 80. Okay? We know something else, because we take the leaching and we poison half the samples. If we poison it, then it's just what carbon is leaching out of the grass. If we let the bacteria grow, we know how much of that carbon is labile and is respired back to CO2 with under 25 days, in a short amount of time. And something like 50 to 90% is respired to the atmosphere. A lot. So then we have, you guys know about tidal creeks? So the creek has a channel, and then a creek bank, and then a marsh platform. And the tide comes up, and it flows into the creek bank and flows out of the creek bank, presumably picking up carbon. It flows in and over the creek bank and fills up the tidal platform, the marsh platform, and flows back out. And some flows over, leaks in, and flies out. It's complicated. So this experiment takes a pipe and sticks it right into the creek bank and puts a pressure sensor at the bottom and says, what happens? Well, the well in the creek goes like this. High tide, low tide, oh, went dry. Should go down here. High tide, low tide, oh, went dry. Should be down here. We put a well 1 meter back from the edge, and we said, high tide, low tide, but there's some resistance of the water draining out. So the water actually looks like this. It doesn't look like this to the creek. So it's still draining out when the water comes back, and it goes back up. So it's draining out, goes back, draining out, goes back up. Okay? Then we take this pipe in the side, and it looks like this. So we can go, okay, we make some calculations, we put in an equation, we put it in a model, Christoph's expertise. Here's this model of how much flow at every different depth. And he can total it up, but he's a modeler. So he says, I don't know how much the difference between what's in the pore water and what's in the creek water. If it's 2,000 millimolar, 2,000 micromolar, 2 millimolar, it would be 50. Remember, the plants were 80, the total is 1,000, 5% of the total. Small amount. But more likely, the difference in concentration of DOC, DIC could add to it, but DOC in the creek bank to the creek is maybe 200 micromolar. So it gives some small number like 5. Okay, so I'll show you all these numbers at the end to summarize. It looks like a budget. Then another student is taking the water that flows over the marsh and says if it flows over the marsh and sits around the plants, bakes the plants leaches the plants for 4 hours or 6 hours, and flows out, using our numbers from the leaching experiment, we get these kinds of numbers, what we call overland flow. It's the flow that goes over the marsh and then comes back down. So we get a number for that. Jay Cable wants to know about groundwater. Groundwater has radon that comes from the rocks in the land. And so she can do a radon transect up and down this small creek. Here's the transect, here's the concentration. It goes up as we go towards the forest to land. You can do an inventory of radon. Radon comes either from groundwater, or from the bottom, the benthos, and it can leak out into the atmosphere. So we can take wind speeds and get piston velocity, so we know how much escape, about half. We know what diffuses from the bottom, which is very small, and the rest is coming from groundwater. And we can estimate the groundwater transport of this system. Fresh groundwater is 1 meters cubed per second. What's the delta C? How much carbon is it adding? Well, the DOC is probably very low, like 0. The groundwater is very low on DOC. DIC could be high. It's all carbonate karsts. So the DIC could be something like 75 of that number. Okay? So what you see is these very different disciplines with very different techniques, all trying to get to a little number that we can try to add together in a budget. We want to know the total flux of carbon just coming out of this creek. So let's just put a net of sensors and measure what's coming out. But the flood tide, everything goes back in. So it comes out and it goes back in. But the tide is low to high. It's not asymmetric. It could be that there's more tide coming in the next one. We have input of carbon into the system. Now we have export. Now I got to go over a month and figure out but there's a storm. It's very difficult. So we put a sensor in the middle of it's not a buoy, it's on a pole, a little sensor at the mouth, and we measured anytime the velocity is going in, what is the CDOM, which is a proxy for DOC. Anytime the water is coming out, what is the CDOM? And we've averaged over a week, many tidal cycles, high tides, low tides, high tides, low, and we didn't care about the volume. We just got a difference which was 1.7 of these fluorescent units, quinine sulfate units. We looked at the discrete samples to know how much fluorescence converted to DOC, which is about 8.5 micromolar difference between the in and the out. And then we used that study of the student who said, what is the tidal amount that goes in and out because of the elevations? We multiplied by that and said that's the amount of flux of water going in and out on average, and times the difference of what goes in and what comes out, and we get 325, which is like 33% of the total net primary productivity is being exported as outwelling carbon. Good number. Okay. The blue carbon people at ASLO wanted to know how much is buried. And so this is another student that looked at lead-210 dating. So she could get mass accumulation rates, sedimentation accumulation rates, and then she looked at the total organic carbon of the sediment, and she could add it up and find that we get numbers that are very similar to other systems around 40 to 100 grams carbon per meter squared per year. So that's 4 to 10% of the net primary productivity is being buried because sea level is rising and the sediments accreting in the system. Then we want to know what happens once the carbon gets offshore. So we stick these are micro buoys. They're little yellow waterproof boxes with a GPS truck tracker. The companies want to know where FedEx or UPS is, and they're not sleeping or whatever, they're driving. So they have truck trackers that tell them every hour where they are. They're very cheap. So you buy it, you stick it in a waterproof box, and you talk to the satellite, and you know where these little things are drifting. And you put 3 or 4 of them out there, and they move back and forth tidally, but slowly they disperse. They spread. We can look at that spread around the middle of them and know something about the dispersion rate, how fast, just like the diffusion rate of the water. And then we can look at the concentration gradient from inshore to offshore and say, I have a gradient, I have a dispersion, and I can make a flux. Okay? So I use that flux, and it comes out to be something like, with some assumptions, 5 to 20 of that total number. Then I noticed that if I have this very high resolution, it's not conservative. Actually, there's photodegradation. It's shallow, it's clear, and the sunlight's coming down and destroying the dissolved organic carbon, breaking it up so the microbes can eat it. And I can look at how much of the deficit there is, and I can know how much that flux is, the amount that's respired in the flats. And then sort of the last, this is not so quantitative yet. It's very preliminary data from Jennifer Sharia and her student Gabrielle Lyons, but she looks at C13. C13 is terrestrial and marine. Okay, so we're going from the forest, the creek, to to the flats, to the ocean. It goes this way. We have 3 sampling points way up the creek, at the creek mouth, and offshore at the flats. Okay, so it sort of looks that way. C14 is the age. So is it fresh plant material, or is it older sediment material? And again, we look from new terrestrial material to old marine material. And it looks consistent with what we're thinking about the processes. So here's our model in our head for the whole thing. We have, on the marsh, we have productivity from the grass as the main one, and we bury some of the carbon there. We have some groundwater coming out and a lot of respiration back to CO2 in the atmosphere. Some of it makes it into the creek as dissolved or particulate organic carbon, or DIC as well. And the timescales are tidal, hours to days. The tidal exchange does it, but also events are very critical. It changes the whole system. But it rains, it flushes a lot of the material out that hasn't been exposed to transport. And there's this seasonal pulse. The fall is different from spring. In the fall, you're getting more stuff coming out. In the creek, I didn't talk about this one, but we actually did an experiment where we resuspended sediment from the creek and shined sunlight on it. It's very strange. And the sunlight photo-dissolves the carbon. So it takes it from the particle and it becomes dissolved organic carbon. A lot of it, like up to 20%. A lot of it. 20% of the total flux. If you do it in the dark, nothing comes off. It's the sunlight somehow reacts with the particles. And then we have this creek washing in and out to the flats. And so we have dissolved organic carbon in particular. And it might be a sink for POC and source for DOC. We know it's a source for DOC over slightly longer time scales, days to weeks. The tidal exchange. And then we realized that these wind events are really critical. So these microbuoys are going in and out. If I get a big wind that comes offshore, it goes 100 kilometers away. The whole carbon just gets pushed out into the ocean. So we have to think about this different with the event scale types of things. Then it gets out here, and I didn't talk at all about seagrasses because I really have no good approach for that. It could be a very significant amount of carbon. It could be also a lot of carbon burial. And then there's a lot of degradation, photobiological degradation combined. So if I put the numbers on that, 100% comes in, carbon fixed from the atmosphere, 4 to 10%, 5% gets buried. Something like 60% goes back into the atmosphere very quickly. Respiration. I have all these numbers for these processes here. The plant leaching could be 80 to 220 or 8 to 20%. The creek bank exchange is probably small. The DIC could be significant. We don't have a lot of DIC numbers yet. The export, this is a good number. 33% comes out of the 100% that is fixed. So outwelling is a significant process. It moves this grass carbon from the marsh to the coastal zone. We might have this large flux from particles to dissolved here with the sediment resuspension. And then we get an additional amount of respiration on the flats that go out. And yet still, something like 6 to 30%, maybe 15% on average, makes it further offshore, makes it out of that system into the Gulf of Mexico. It's a very nice sort of mental image of how the carbon moves from place to place, how much goes up, how much gets fixed. And then we're still looking at what's the composition of the carbon in these different areas. So questions on this? Yes. Yes. Mm-hmm. Uh-huh. Yeah. Hmm? Yeah. Mm-hmm. Yeah. So there's very good points. And the seagrass productivity is very high. And so we could be importing a lot of the seagrass carbon into the creek and either sedimenting it or photodegrading it and coming out. And so that's where this, the net amount is coming out. But we don't know if the composition is shifting. So really, Jennifer Sherry is beginning to look at the chemical analysis of the amino acids and the bacteria, who's using what, and the isotopes. We weren't expecting the seagrasses when we wrote the proposal. We got out and go, whoa, look at this. What do we do about this? And it was complicated enough without getting that far. But it needs to be looked at, for sure. The microphytobenthos we're worrying about. And I have this is a very dense grass area, so it probably is not significant in this site. But I do have a student who's made an experiment that takes a core of the grass with the sediment and the microphytobenthos, everything in there, pours water on top, and it turns out it doesn't really trickle in. It just sits there, and then she pulls it back out, and it increases significantly. So that is integrative of the plants and the surface sediment. So if we just do the plants, and then we do the plants and the surface sediment, we might assume it's sediment-water interaction plus microphytobenthos. And it's significant. The total is significant. We don't know how to divide up the two. I guess we go at different seasons or something, or different densities. Good idea. Complicated. There's other things about this, like the water budget doesn't even work. So you go sometimes, and as you go into the creek, the seat dom and DOC go up, but the salinity also goes up. Why? Evapotranspiration. The plants are pulling the salt, the fresh water out and leaving the salt. It's a very strange system. So I have tons of ideas about, in fact, we wrote a report on ocean literacy. We wrote the standards for ocean literacy. We have a whole CD of activities that I can share with you. And then we wrote the report on where ocean literacy is internationally. And so I'm happy to talk to you about ocean education, ocean literacy, ocean outreach. I do a lot of this work. And some of the ideas, it's mostly just a teaching workshop this afternoon, but the ideas will be presented this afternoon. It's just an hour. I sometimes do a whole day. But to sort of summarize the, to just summarize this talk, coastal systems are complex. There's lots of processes from lots of different disciplines at lots of different temporal and spatial scales. And it's enough to, you have to go to the local expert to say, so do you understand this system? Oh, I know this, and I know this, and you want to work with the locals, but then you want to step back and try to make some general ideas about salt marshes, mangroves, estuaries, something. We really need to study the dynamics of this, sensors and sensor networks. Otherwise, we can't even see the processes. So we have the big-scale eco-shuttle, the smaller-scale mini-shuttle. We have, I didn't even talk about these river monitors that we put in, these cellular networks, the buoys. If we want to scale up, we somehow have to use remote sensing because we can't put these sensors in all the systems. We have to think, that one looks like that one. Classify that one as the same, and that would be the flux or the whatever it is. We need models to fill in all the details between all the studies and the remote sensing and get to the processes underneath just the surface of the remote sensing. And we need models to help predict. So once we can understand the effect of land use, the effect of climate change, the effect of temperature, we can predict how these systems will change in the future. And we're continuing to 1 to 2% loss of salt marshes per year. We're continuing to affect the coastal zones, both in small areas, developing an area and destroying an area, getting rid of a salt marsh, putting in a whatever, and to predict how and value the natural systems. It's not just a value because it's a salt marsh. I don't like a salt marsh. It's dirty. It smells. It's sequestering and storing carbon for you. It's preventing flooding. It's providing biodiversity and food, nursery. You can add up the value and then, maybe we really should protect that as opposed to destroy it. So with that, I'll end and take any questions. Thank you for your attention.
Thank you, Robert. Is there any question? Remember that you must switch on the button in the microphone. Any question? Yes, Ed.
In terms of remote sensing, I saw there's some good work on extracting CDOM from remote sensing data as well. Any feelings on types of sensors, new satellites and sensors that are more specific for that?
So the more you have hyperspectral and the more you get into the blue towards the UV, the better. and they're getting better with that. There's different zones, like this is an estuarine zone, there's a coastal zone, and so you have different algorithms for that. The tricky part, though, is getting the resolution. So the ocean sensors are a kilometer to 200 meters now. The land, what I showed, the Worldview 2, is 2 meters. So you can do land at 2 meters, but can you do water at 2 meters? So we need to have more sensitive sensors with more of the UV wavelengths at the higher resolution. Landsat 8 we're playing with now is 30-meter resolution. We're looking at Boston Harbor with Landsat because we have a record of the water quality from 1991. So that's 25 years in the back. And we have Landsat 8 going forward, which I think can be used because the gradients are so high and the concentrations are so high, we can look forward. So I've got a remote sensing team and a buoy team and a water quality team to look at, trying to look at this story of Boston Harbor over 30 years with Landsat 8. But getting better. It might have to change with different systems and different seasons, and so you have to adjust your algorithms to make sure that, but the gradients are so large in the coastal zone that I think we have a hope to do that. You can't use the 200-meter ones because it's just too big, but 30 meters is beginning to get better. It's only going to get better.
Okay. Maybe you might know that Gloria and Ed are leading a project, a European project with many similarities with, at least with the third example you have given us. Mm-hmm. Okay, any other question?
Now my question is that what kind of sediment do you have in these salt marshes? Because I know that you show some example of ship age, mm-hmm. and the ship age looks like really important. But in our case here in the Cadiz Bay, the question is that the salt marshes are really, really muddy. Mm-hmm. And the question is that I think we don't have any really big importance of the seepage water mm-hmm. coming to the.
So we're trying to study that. The Neponset is very fine grained, and the water's just not going in and not coming out. So there's sort of there's a lot of interesting things about the Neponset. So there's other areas. So we have these creeks that go in and come out, but then there's these I call them pipes. You know about the pipes. So there's a whole subsurface network of where the water can flow. And so we don't sample those because we have to find them first and then sample differently than the rest. And then there's what we call rivulets. So the creek flows out and then continues to creep out. And so then we put a sensor in the rivulet and the carbon is higher. And it flows for about 2 or 3 hours and then stops. The flow is very small. Concentration is higher. It looks, at least preliminarily, consistent with what's seeping out and the time delay of the seepage. So the seepage comes into the river. So we understand that, but we don't know anything about these pipes. So that could be a whole other set of numbers that are interesting to study. The sediments in Florida are more sandy, and so I don't believe the model that it goes so far as they say. But we need to know. But the sediments towards the forest and the sediments at the creek edge are different. And so it turns out that there's a lot of sediment accumulation at the forest edge, but not much organic carbon. And then you get to the other side, you have not so much mineral sediment. It's all peat, so it's high organic carbon. And when you balance the two out, the burial is about the same. Higher accumulation, low TOC, lower accumulation, high TOC, and something like the same. Maybe in the middle is the highest. But it very much matters what the sediment type is. Yeah.
Another question? Regarding the first example you gave us, I have missed in your research team people analyzing the plankton community. When you show with us this subsurface maximum of chlorophyll and an accumulation of organisms, do any of you analyze it in the microscope? No.
We didn't know. We did have on the boat a microbiologist.
Okay.
So she didn't do any genetic anything, but we did microbial incubations of the water. So we took the water and we exposed it to microbes or no microbes, and sunlight and no sunlight. And we know compositionally it's different from the other water, but we don't know what's doing it. Okay. And the phytoplankton, the only thing that we did was we modeled the light fields. Uh-huh. And in fact, there was enough light, 1% or so, on the bench that could have had low but active photosynthesis. So it could be that the phytoplankton are doing some. We suspect it's the microbes because of these filtration and experiments, but there could have been direct input from phytoplankton. But we don't know who.
Okay, so thank you very much for coming. And I remember everybody that this afternoon at, I don't remember, Javier? At 5.
I think it's 5:30?
5:30.
Sorry, 4 is a...
My turn.
Class, yeah.
5:30 at the
we have the second lesson from Robert Chen that I invite all of you to come. Thank you. Thank you.
Thank you.